Thanks for coming out to my talk. Let's start with who am I? Well, I'm 18 years old. I'm a sophomore at the Rochester Institute of Technology. I love Windows internals. I'm mostly self-taught with a strong mentor group helping me along the way. And I have a strong game hacking background, which is why I'm involved with Windows internals. So let's begin with, what is this talk about? Well, in this talk, we're going to be going over loading a rootkit, communicating with a rootkit, abusing legitimate network communications, an example rootkit I wrote called the Spectre rootkit, and the design choices behind it, executing commands from kernel, and tricks to cover up the file system trace of your rootkit. So let's begin with Windows rootkit overview. Well, when I say rootkit in this presentation, I'm going to be referring to kernel level rootkits on Windows. So why would you want to use a rootkit? Well, kernel drivers have significant access to the machine. Unlike in user mode, you pretty much have access to anything and everything. Kernel drivers run at the same privilege level as a typical kernel antivirus. So this means that, generally speaking, you have the same access to the same resources. There are less mitigations and security solutions targeting kernel malware. If you can load kernel code, chances are you can do a lot to cover up your tracks. Antivirus often have less visibility into the operations performed by kernel drivers. This is because antivirus often depend on using user mode hooks to gain visibility into certain suspicious operations. But in the kernel, you can't directly hook Antos kernel because of PatchGuard. Finally, kernel drivers are often ignored by antivirus. Let's take a look at an example of that. So whether you're running a consumer antivirus or a corporate EDR, chances are that the application you use will treat kernel drivers with a significant amount of trust. For example, here we have the pre-processed thread callbacks from both Malwarebytes and Carbon Black. So these functions are called whenever a handle is created or duplicated to a process or a thread. Starting with Malwarebytes, what they do in their callback is check to see if the process ID is less than 8. And if the handle is for a kernel handle, then it will just go ahead and return 0 and stop processing there. For Carbon Black, they take a little bit of a different perspective. If the handle is for a kernel handle, or if the previous mode is not user mode, then it will not process that handle creation. So let's talk a little bit about loading a rootkit. Well, there are a lot of vulnerable drivers. With some reversing knowledge, finding a 0-day in a driver can also be trivial. Some examples include Capcom's anti-cheat driver, Intel's Now driver, and even Microsoft themselves. Now, the reason I put vulnerable and 0-day in quotes is because oftentimes drivers require administrative privileges to communicate with them. Following Microsoft standards, Ring 3 with administrator to Ring 0 is not a valid security boundary. So technically, it isn't even a vulnerability. But this doesn't mean we can't abuse it either. So using legitimate drivers has quite a few benefits too, because you only need a few primitives to escalate privileges. And finding a vulnerable driver is relatively trivial. A great place to start is OEM drivers. And it's very difficult to detect some operations due to compatibility reasons. For example, let's say that a driver exposes some suspicious operations over its iOctl interface. Especially if the legitimate application uses that suspicious functionality, it can be very difficult for an antivirus to discern whether or not an operation is from a legitimate application, and this is just intended use, or if a malicious application is abusing that driver functionality. Now, abusing legitimate drivers does have some strong drawbacks as well. One of the only reasons I don't really like this method is because, let's say you use a legitimate driver to load your own driver. The problem with this is that you can often run into compatibility issues, especially across operating system versions. But even if we're trying to get rid of all the bugs, you're going to probably run into some edge cases that can cause blue screens. And the last thing I want to do is blue screen a victim. For some red teamers, an option is just buy your own certificate for your company. Now, this is great for targeted attacks. You're not going to have stability concerns, but it potentially reveals your identity, and it can be blacklisted. Now, this blacklisting doesn't really happen so much these days. It's something that's being worked on by AV vendors, but it's very possible that a red team company might have their certificate blacklisted because it's strictly associated with kernel malware. Another option is just use someone else's certificate, and there's actually quite a few publicly leaked certificates available to download. If you're looking for one, A good place to start is cheating forums, which have quite a few posted. There's almost all of the benefits of using your own certificate, except without de-anonymizing yourself. But the leaked certificate you use can be detected in the future, especially if it's a very public one. If the leaked certificate was issued after July 29th, 2015, it won't work for kernel drivers on Windows machines over version 1607 that have secure boot enabled. So in most cases, Windows doesn't actually care if your driver has been expired or revoked. So what you see in digital signatures is not what the kernel code signing policy is. So even if you see, this certificate has been revoked or this certificate has been expired, I'd still give it a try because chances are it's going to work for kernel drivers. So several leaked certificates are already publicly posted, but it's not impossible to find your own either. For example, this website called Grey Hat Warfare allows me to search open S3 buckets for files. When I search for PFX and P12 files, common extensions for private keys, I found over 6,000 results. And the best part about this method is that at this time, the bulk of antivirus don't even come near detecting this method. This is because I guess they haven't been working on blacklisting as much, but I have not seen any antivirus yet detect most leaked certificates I've come across. So let's talk about communicating with a rootkit. Well, a tried and true method is just to beacon out to a C2. Now, firewalls can block or flag outgoing requests that are to suspicious IPs or ports. And even for the more advanced techniques, there's new features such as advanced network inspection that try to combat them. Another option is just to open a port onto your victim machine and have the C2 connect to the victim. Now, the problem with this is that even though it's relatively simple to set up, it can be blocked by our firewall, and it can be difficult to blend in with the noise. So another option for more advanced actors I've seen is application-specific hooking. This is where you piggyback on one application-specific communication channel to receive communications directly from the C2. Now, this is incredibly difficult to detect, especially if it's using a legitimate protocol, but it's not very flexible because if the machine you're infecting doesn't have that one service exposed, then you're going to be out of luck unless you have backup communication methods exposed as well. So what I wanted was a method that had limited detection vectors, flexibility for a variety of environments, and my assumptions were that victim machines will have some services exposed, which is especially true for corporate environments. And inbound and outbound access may be monitored as well. So application-specific hooking was perfect for my needs, except for the flexibility. Is there any way we can change application-specific hooking to where it isn't dependent on any single application? Well, what if instead of hooking an application directly, we hooked network communication, similar to tools such as Wireshark? Then what we would do is we'd create these malicious packets in our C2 and insert a magic constant value that the malware is aware of as well. Then we send this malicious packet over to any legitimate port on the victim machine. Since our malware is intercepting all packets being received, it also constantly searches these packets for the magic constant that the C2 inserted. So what we can do is we can piggyback off of all legitimate communication channels by simply abusing the fact of intercepting all packets. Because what we can do is, again, from the C2 to the victim, any open port, and with that magic constant, the malware then knows that packet is from the C2, and it can process out other data from it. So let's talk about how we would hook the user mode network stack. So a significant amount of services on Windows can be found in user mode, but how can we globally intercept this traffic? Well, networking relating to WinSocket is handled by AFD.sys, otherwise known as the ancillary function driver for WinSock. Reversing a few functions inside of mswsock.dll revealed that they're using an ioctl interface by the AFD driver to communicate. Now, if we could intercept these requests, we could snoop in on the data being received. So when you call NT-device IO control file, how does the kernel know what function to call? Well, first, it gets the device object associated with the file object by calling IO get related device object. This is, for our purposes, just going to be retrieving the device object member of the file object. If the driver supports fast IO, it'll dispatch the request using the fast IO dispatch table of the driver object. If it doesn't support fast IO, then what it'll do is allocate and fill out an IRP, and then use IO call driver to dispatch the IRP. So let's talk about standard methods of intercepting ERPs. So the few common methods include, so in the driver object, there is this major function array. Now this major function array, it contains pointers to dispatch functions, and the index for this array corresponds to the major function code. So let's say we want to hook a specific major function code. Well, what we would do is we would go into the major function array, and for that index, replace the dispatch function pointer to our own dispatch function. Another option is to just perform a code hook directly on the dispatch handler. So for picking a method, there are a few common questions you should ask yourself. How many detection vectors are you potentially exposed to? How usable is the method from a stability and compatibility perspective? And how expensive would it be to detect that method? So for hooking a driver object's major function table, you're going to be exposing yourself to memory artifacts. From a usability perspective, it's going to be quite stable because driver objects are well documented and easy to find. Finally, for how expensive is it to detect? Well, it's not going to be that expensive because if you think about it, all an antivirus would need to do is enumerate the loaded drivers and check their major function table for any patches. So for code hooking, you're going to be exposing yourself to memory artifacts. And unless the function is exported, you're going to need to find a function yourself. Now the problem with this is present, especially if the driver file changes between operating system versions. And also, not all drivers are going to be compatible with this code hook because of PatchGuard. And if HVCI is enabled, this method won't be viable at all. For how expensive is it to detect? Well, it's potentially inexpensive because there's so many different ways to detect hooking. For example, if an antivirus implemented a generic detection functionality where they would enumerate the executable sections for loaded drivers with what's on disk, now that's quite expensive, but if they know that you're hooking a specific function of a specific driver, then checking the first few bytes isn't going to be very expensive at all. So I wanted a method that was undocumented, stable, and relatively expensive to detect. Well, what if instead of hooking the original driver object, we hooked the file object instead? So what I'm talking about is, well, the device retrieved for a file object is going to end up being the device object pointer inside of that file object. So what is actually stopping us from overriding this pointer of that one file object with our own? Well, it turns out absolutely nothing. So what we can do is create our own device and driver object, patch our copy of the driver object. So this is not the same thing as patching the original driver object, which can be easily found. This is patching our own copy. Then we can replace the device object pointer of the file object we're hooking with our own device. The neat thing with this method is that instead of hooking globally for every different ERP from any process, we specifically hook the specific handle we'd like to hook. Let's talk about how we would actually do this. Well, we need to first find file objects to hook. And the way we can do this is through the great API called ZW Query System Information, which exposes a variety of information about your system. Now, one of the classes you can request is the System Handle Information class, which will allow you to query all handles on a system, including the process ID behind that handle and the kernel pointer for the object that that handle points to. Now, if we open the AFD device ourselves before scanning for these file objects, we can easily determine if a file object is for the AFD device by comparing the device object member of the file object with the AFD device we already retrieved. So before we can overwrite the device object member, we need to actually create our fake objects. And fortunately, the kernel actually exports the function it uses to create these objects itself. So all we need to do is call obcreateObject, the IO device object type, an IO driver object type, depending on what object you're creating. Once you've created the objects, you can just simply copy over the existing values. So with our fake objects created, we're almost ready to set the device object of our file object. But first, we need to hook our driver object. Now, the way we're going to do this is again by using that standard hook a driver object method, but except we are not performing it on the original driver object. This is our own copy, which an antivirus cannot easily retrieve. So to prevent race conditions while replacing the device object member, the original device object we use inside of our hooked dispatch function needs to be set at the same time that we replace the device object of the file object. So the way I did this is by simply using interlocked exchange. So now that we've hooked our file object, there's not much work left. So in our dispatch hook, if the major function code that is being called is hooked, then we should pass the original dispatch function, the original device object, and the ERP to the hooked function. Then, if the major function code ERP major function cleanup is requested, then we need to replace the device object member of the file object with the original device. This is to prevent any issues during teardown. So how many detection vectors are you potentially exposed to? Well, it's going to be memory artifacts. And how usable is the method? Well, since most of the functions we use are at least semi-documented, they're probably not going to change too much. How expensive would it be to detect the method? Well, it's also going to be pretty expensive because an antivirus would have to replicate our hooking process and scan each file object to see if its device object has been patched. Let's talk about how the Spectre rootkit abuses the user mode network stack. So, using the file object hook, we can now intercept ERPs to the AFD driver. This allows us to intercept all user mode networking traffic and send and receive our own data over any socket. So to review, our existing plan is to hook network communication in our malware that is on the victim machine, similar to tools such as Wireshark, and then we place a special indicator in the packets we create in our C2. Then when this packet is sent, the malware scans for that magic constant and then recognizes that magic constant, and it parses out any extra data that that packet might have. But how can we actually retrieve the content of packets that are received? Just because we intercept AFD communication doesn't mean we have immediate access to those buffers. So for receive operations, an ioctl code ioctl AFD receive is sent to the AFD driver. Here's the structures that are sent to the input buffer. Now the AFD receive info structure is the one that's actually sent, and it has some flags and an array of buffers. This array of buffers is what actually contains the content of the data that was received. Let's talk about how the Spectre rootkit was designed, specifically the packet structure that gets sent from the C2 to any legitimate port. Well, the packet structure allows you to prepend any data you want, as long as it isn't the magic value. Then you can have your magic constant, and what you can do is this magic constant will act as a reference point for the rest of the structures. After the magic constant, you're going to have a base packet structure, which is seen on the right as well. And all it contains is the packet length and the packet operation being requested. After the base packet structure is an optional custom structure. Now this custom structure will vary or may not even exist, depending on the type of operation being requested. After the custom structure, you can append any data you'd like. The idea is with this packet structure is that you can send any packets you'd like before the malicious packet or after the malicious packet, and even in the malicious packet itself, you can prepend or append any data you'd like besides the magic value. So once a packet is received by the malware, what it does is it'll search the buffer received for the magic value. And if the buffer contains the magic, it'll go ahead and pass it along for processing. If it does not, it'll simply ignore the packet. For processing, it'll check to see if there's enough bytes to fill out a base packet structure in the already received data. If there is enough bytes, it'll use the check to see if there's enough bytes for the custom structure, if there is one. Only when both of these base packet and the optional custom structure is fulfilled will it dispatch the packet. If in any case it needs to get extra bytes, it'll go ahead and receive it using the socket handle. So before we go any further, let's also talk about packet handlers in the Spectre rootkit. So the Spectre rootkit contains a general packet handler class that exposes a virtual process packet function. Now this base packet handler class has a default constructor that accepts a pointer to the current packet dispatcher instance. And the process packet function below it accepts a pointer to the current packet. We'll talk about the dispatcher in a later slide. So an example of a packet handler included with the Spectre rootkit is the ping packet handler. Now this handler is used specifically to determine if a machine or port is infected. Now the incoming packet has no actual data other than indicating that its type is a ping, and that the handler responds to the client or the C2 with just another empty base packet with this type set to ping. So once packet is completely populated during dispatching, the packet dispatcher will allocate a packet handler depending on the type of operation being requested. it'll call the packet handler's process packet function, and then it'll free the packet handler once it's done. Now, the reason the packet dispatcher is really awesome is because since it passes a pointer to itself to packet handlers, what can happen is that the packet handler can redispatch recursively a brand new packet. So the best way I can explain this is through an example. So let's talk about the XOR packet handler included with the Spectre rootkit. The XOR packet handler takes in a XOR packet structure, and this structure contains a XOR key and a XOR content. So what the C2 does is, let's say it wants to request some operation. It'll take the bytes of that base packet in an optional custom structure and stick it into the XOR content array. Then, it'll generate a random byte in place of the XOR key, and use this random byte to perform a XOR operation on each byte of the XOR content. When the XOR packet is received by the malware, it'll use a XOR key to deobfuscate the XOR content, and then what it'll do is call the dispatch function again, except it'll pass the XOR content as the new packet to dispatch. So to explain this is pretty simple. The Spectre rootkit allows you to create infinite layers of encapsulation. Now this is great because, for example, if you create a few different type of packet handlers, such as XOR packet handler, you can create layers of obfuscation and change the bytes of packets randomly, and allowing you to add entropy even if you're requesting the same operation. Another common feature seen in kernel malware, malware in general, is executing commands. But before we can actually execute commands in the kernel, we need to understand, how do you execute commands in user mode? Well, to follow a basic example, first, you need to create pipes for your output. Now, this is going to have a read and write handle to this new pipe, and you can just use the create pipe function for this. Then, you're going to create a startup info structure. And in the structure, you're going to set the standard error and standard output handles to the unnamed pipe you just created. And you can also set window flags, such as hide the window, so that the victim doesn't see the command prompt window being created. Once you set those structures, you just can call create process, and you can wait for it to exit using wait for a single object. Once the process is exited, you can retrieve the output of the process by calling read file on the unnamed pipe. So first, let's begin by re-implementing the create pipe function. So what the create pipe function does in the background is it'll check if the device named pipe is already opened. If it is not, it'll go ahead and open it. Then it'll set the root directory for the object attributes for the brand new pipe to this named pipe device. When it calls ntcreate named pipe file, it'll use the access rights generic read, because this function creates both a read handle and a write handle. Once the pipe is created, it'll call nt-open file with the root directory set to this brand new pipe. This is used to obtain a write handle for that pipe. So once we have the pipes, we just need to create the actual process, and we'll be using ZW create user process because that's what the kernel 32 API uses itself. The first thing you need to do is generate an attribute list. Now the attribute we're going to set is just a PS attribute image name, which represents the image file name for the new process. Next, we have to set an RTL user process parameter structure for the new process. And in this, it's very similar to the startup info structure we saw in user mode, except we have to specify a little bit more information. So besides the window flags and the output handles to our pipes, we need to specify the current directory, the command line arguments, the process image path, and the default desktop name. From there, all it takes is a call to ZW create user process to start the process. And once the process has exited, similar to what we do in user mode, we can just call ZW read file to read the output of the process. So let's talk a little bit about hiding a rootkit. I'd like to introduce you to mini filters. So what mini filter drivers allow you to do is attach to volumes and intercept certain file I/O. This is performed by registering with the filter manager driver. So to give an example from Microsoft, when a user requests file I/O, when it's sent to the file system, the filter manager driver will actually intercept this request, and then it will pass it along to the mini filters that have registered with it. These mini filters have a lot of control, and they can even edit or modify the file request. Once it's been edited or just passed through all the mini filters, it's then sent to the file system. So mini filters can be useful to mask the presence of our rootkit. For example, a mini filter can redirect all file access for a certain file to another one. So we can use this to redirect access from our rootkit file to a legitimate driver file. So again, going back to the previous picking a method slide, we were concerned about detection vectors, how usable is the method, and how expensive is it to detect. The easiest way to abuse functionality of a mini filter is to become one yourself. Here's the minimum requirements for FLT register filter. First, you create an instances key under the service key. Then under the instances key, you create an instance name key. This can be any name you'd like. You'll use this name for step 3 when you create a default instance value under the instances key, and you set this name to the string value to the name you used in step 2. And finally, in step 4, under the instance name key, we'll add the altitude and flags values. So how many detection vectors are you potentially exposed to? Well, you're going to be exposing yourself to registry and memory artifacts. How usable is the method? There's no concerns from a stability or usability perspective because this is how legitimate drivers register as a mini filter. But how expensive is it to detect? Well, besides the registry artifacts, you're going to be easily enumerable through functions such as FLT enumerate filters. And also, filters can be enumerated from user mode with administrative privileges. So really, it's not that expensive to detect. So another method is to just simply hook an existing mini filter. And there's a couple of routes you can take. You can code hook an existing callback, or you can overwrite the FLT registration structure that is used in the call to FLT register filter before that function is actually called. Or you can decom an existing filter instance and replace the original callback with yours. So again, one of the easiest ways of intercepting callbacks is just perform a code hook. But there's going to be quite a few drawbacks, even if you did something as simple as a jump hook. You're going to be exposing yourself to memory artifacts. You're going to need to find a function yourself. It's not compatible with PatchGuard or HVCI. And it's going to be pretty easy to detect to you because there's just so many different ways of detecting hooking. So another semi-documented method of hooking is using an existing mini filter. So what you can do is you can enumerate filters in their instances using FLT enumerate filters and FLT enumerate instances. The function that gets called for a certain operation is specified in the FLT instance structure. So this FLT instance structure has this callback nodes array. And what this array contains is the pre-operation and post-operation, depending on the array index, which is associated with the major function. So what you can do is you can find the FLT instance by first enumerating filters and then enumerating instances for that filter. And if there's a callback node you'd like to replace, you just simply set the pre-operation or post-operation function to your own. Now, a note with this is that you're going to also want to patch the FLT filter structure as well, which contains an FLT registration structure. This is because you don't want to leave any traces of your hooking. So what you're going to want to do is inside of that registration structure, inside of the filter structure, is replace the pre-operation or post-operation there as well. Now, this doesn't have any actual impact other than making sure that the values align with the function that you're hooking. So how many detection vectors are you potentially exposed to? Well, you're going to be potentially exposed to memory artifacts. How usable is the method? Now, since finding an FLT instance is semi-documented, it's going to be pretty stable, but the FLT instance structure itself is undocumented, so that can change randomly as well. How expensive is it to detect? It's going to be still relatively inexpensive because an antivirus can enumerate these filters in their instances and then check to see if any of the functions are outside of the bounds of the driver. So let's say you have a mini filter and you like to abuse it. What's an example of that? Well, what you can do is inside of the pre-create callback, you can use FLT get name information to get the path of the file being accessed. If a path contains a protected file, you can replace that file name using IO replace file object name. Then, if you return status reparse, what will happen is that file access will be redirected to that brand new file. And so what we can do is then when a person accesses our rootkit on the file system, we can then redirect it to another legitimate driver so that it appears to be legitimate. All right, so wrapping up, I'd like to give thanks to Alex Ionescu, who's been a longtime mentor and is very experienced with Windows internals. React OS, because their documentation and source code is fantastic when you're reversing Windows itself. Nemanja Milezmagic and Vlad Ionescu, who helped review this presentation. So thank you so much for coming to my talk during these hard times, and I appreciate you coming out. If you'd like to follow me on Twitter, that's my Twitter handle. Check out my blog, and if you'd like to check out the Spectre rootkit, there's a link available. Hopefully it'll work. Hi there, guys, and thanks for coming out to my talk. I'll be answering questions in chat now, and if you ever want to reach out with any more, feel free to contact me over Twitter or by email.